Okay, hey folks, so I'll be doing a little tutorial here about, or rather an introduction to norms. These kind of show up all over in mathematics and lots of different machine learning topics, as well as optimization in general. Norms are one of the things that I didn't really learn about in my undergraduate studies, and it was a pretty big wake-up call when I started grad school, because they kind of show up everywhere and are extremely useful. So before I can talk about norms, I really need to talk about what a metric is. So we have this thing called a metric, and what that is going to allow us to do is to quantify the distance between 2 points. And I'm putting the distance in quotes because there are lots of different ways to quantify that between 2 points. So if we have 2 points here, which I will denote in this way, so this is a vector x, that's why it has the underline shown here, and it has components x1 through xn, and we can do a vector y, which has components y1 through yn. If we want to talk about the distance between these 2 points, we would define a function that we're going to call a metric. So I'm going to call it d, right? And it's going to take a vector x and a vector y, and then it is going to give us the distance between x and y. If we have a coordinate system that looks something like this, right? And we have our point x here, and we have our point y up here, what are the different ways that we can talk about the distance between these 2 points? So the one you're probably most familiar with is Euclidean distance, right? So that's just kind of like an as the crow flies from this x to this y. That makes sense. But perhaps these are 2 points on gridded streets, so like a city street. So you can't go through buildings as the crow flies from x to y. So you're going to need to travel up in parallel with this axis, right? And then you'll have to travel over here parallel to this axis. That's another way of measuring the distance. Sometimes this is called the Manhattan distance because of its relation to walking around in city streets. There are, many other ways to measure distance, but one of the other ones I'm going to talk about is the maximum difference between their components. So in this case, it looks here like this distance. So this like lateral distance left to right is a little longer than this vertical distance. So this could also be a way to measure the distance between x and y. So here's the very interesting thing. So this one right here, we'll be talking about norms in a second, but this one right here corresponds to the L2 norm. And so a norm is going to be denoted by these double bars on either side. So this Euclidean distance corresponds to the L2 norm. This distance up here, where we're talking about, walking this measure up and this measure to the right, this corresponds to our L1 norm. And then this right here, where we're taking the maximum, difference of components, this is our infinity norm. So this is kind of going to bring me into talking about norms themselves. A norm is pretty related to a metric, right? So when we were looking at a metric, we're looking at the distance between 2 points. When we're talking about a norm, we're trying to quantify the size of a vector. And again, I'm putting size in quotes because there are many different ways to quantify this. The way that the Euclidean distance of this right here corresponds to the L2 norm is going to be like this. So if our metric is the Euclidean distance, we've got this d of x and y, right? This is going to equal x minus y, and we're going to take the L2 norm of this. So in these cases, basically, if we subtract these points, we get a vector, and we can quantify the size of that vector using a norm. And the size of that vector also corresponds to the distance between the 2 points. These norms that we have talked about, we have an L1 norm, right? So if we take the L1 norm of x, what we're going to get is the sum over each of these components, the absolute value rather of each of these components. Pretty simple. So that's corresponding to, walking up and walking right on like a grid if you need or you're restricted to walk in that scenario. Now we have the L2 norm, and that is going to be this. So we've got xi squared. Now let me clean up that 2 a little bit here, and then we do the square root of the sum of the squares. So this is probably what you're used to, right? So if we're talking about finding the hypotenuse of this triangle, which is the distance between x and y, we say c squared equals a squared plus b squared, right? If we're trying to find the hypotenuse of a triangle. And so we know that this is going to be the length of that hypotenuse. You're taking the L2 norm between, in this case, this point x and this point y. And then the infinity norm is kind of interesting here. This one is going to be defined as follows. We're going to take the maximum of the absolute value of each of these components. And that is shown by this distance here. So our general formula for what we would call a p norm, so where like in this p equals 1, p equals 2, p equals infinity. So if we were to denote a p norm, the sum over all of our components of the absolute value right here to the p, right? And then we take the whole thing to the 1 divided by p. So that's kind of where our square root comes from in this L2 norm. So that's kind of the general formula. And then you can kind of convince yourself that as p moves toward infinity, you're going to get this maximum stuff here. Because the largest component is going to dominate this, and that's why we just take the maximum for the infinity norm. So these are kind of the pretty standard norms that you would talk about. And they're incredibly useful. So, one of the major things, at least as relates to what class we're in, is linear regression. In linear regression, the optimization problem that you're solving is you're trying to find this coefficient. You're trying to find the best coefficient vector here, right? And that's I'm going to define by beta. And the one that we want to pick is going to occur from this kind of decision rule here, where we have this vector beta, right? And then squared. So this is what we've talked about in class. And so definitely pay attention to the fact that this x sub I is not a component as I've defined them previously. Each of these are vectors. That's why there is a bar underneath them here, so don't get confused with that. This is what we had been doing before. We're trying to pick the coefficient vector such that it reduces the difference between our predicted value shown here and our actual value shown here from each of our data points. So basically what we are doing here is we are minimizing the square of the L2 norm. And in the case of linear regression, that is the optimal thing to do. Another thing that we've talked about in class that is related to this are ridge regression and lasso regression. These two things are related to L2 regularization and L1 regularization. Basically what you're doing in each of these scenarios is, in addition to this minimization that we're talking about, we add a penalty for the norm of this coefficients vector. So in L2 regularization, we are using the L2 norm. In L1 regularization, or lasso regression, we are using the L1 norm. Or rather, the square of the L2 norm. in L2 regularization. But it is simple to note that if you're minimizing the square of the L2 norm, you get the same result as minimizing the L2 norm. So what does that kind of look like in practice? So I've got these two graphs here. These come from a convex optimization textbook written by Stephen Boyd at Stanford, and he releases all of his slides online, which is pretty cool. So this top graph that we're looking at is kind of describing the behavior of L1 regularization, and this bottom graph is describing the behavior of L2 regularization. So think about these bars here as showing components of this beta vector. When we're performing L1 regularization, we're going to push as many of the components of this beta vector to 0. And the reason for that is we continue to get benefits using the L1 norm all the way to 0. Conversely, if we're talking about L2 regularization, as you can see here, we have this kind of large chunk of components of beta that are not quite at 0 but are very small. The reason for that is this curve kind of flattens out as it gets closer to 0, so there really isn't an incentive to push them all the way to 0. Another thing to note is in L1 regularization we have these pretty large values over here, whereas in L2 regularization we would gain a pretty significant penalty for values that are that far away because of the fact that it's squared. The final thing I'm going to talk about are what is called a norm ball. These are pretty interesting. We glanced on them a little bit in class. So basically, if you set a specific norm, right, I'm not going to define which one it is yet. If you set a specific norm of a vector to equal 1, what kind of shapes can you draw? That's basically what a norm ball is. If we are looking at the L2 norm ball, where the L2 norm of x is restricted to 1, it's pretty simple, right? Where we're going to be looking at a circle. So that's pretty obvious, right? So if our point out here is x, right, the norm of that is going to be the distance from x to the center. Or if we restrict that to be 1, we can kind of just spin it around, and then you get a circle with radius 1. Cool. Things get a little more interesting when we start talking about an L1 norm ball. Okay, so now we are restricting the L1 norm to be 1. That is going to create different behavior. What that is going to do is it's going to give us this diamond shape, right, where this value is 1, this value is 1. So that's going to give you this diamond shape. And as we talked about in class, this diamond shape can kind of give you some intuition into how the L1 norm, when we're talking about lasso regression, this kind of describes its behavior on how it's pushing components to be 0. So if you do an optimization problem, one of the things that happens is if this is your feasible space here, the optimization problem is often or almost always going to push things toward the corners. And so that is how you're ending up with, a value of 0 in one of those components and a value of 1 in the other component. And then, if we're going to talk about an infinity norm ball, where we are restricting the norm of this and the infinity norm of this vector to be 1, this one is going to be a square, where this value right here is 1, this value right here is 1 as well. And so that would then, change how you're optimizing, because in the same way you're going to then get pushed to these corners, which is going to create a different result in your optimization. So that is all I was going to cover in this video. That's kind of like a general overview of what a metric is and what a norm is. Hope you enjoyed it. Thanks.